We are talking about transistors being smaller than you think because that smallness is exactly why your expensive AI hardware might underperform expectations. The real problem is that shrinking physics has hit hard limits where bigger chips no longer mean faster results, only hotter and less reliable ones. By the end of this video, you will understand how these physical constraints force a shift from raw speed to smarter data placement in modern chip design. For decades, engineers followed Moore's law with absolute confidence. The rule was simple: shrink transistors, double performance every 2 years. This worked perfectly for general computing tasks like word processing or web browsing. But artificial intelligence changed the game entirely by demanding constant, massive parallelism and moving terabytes of data per second. When you push that much logic onto a shrinking die, physics stops being an ally and becomes your enemy. The heat generated does not just make chips warm, it accelerates aging mechanisms like negative bias temperature instability and electromigration at alarming rates. Here is the thing about those physical limits. As transistor density increases to sustain performance, sustained workloads begin to trigger silent data errors in critical tasks like convolutional neural network training. These are errors where the math produces wrong results without any crash or warning sign because a single bit flipped due to heat stress. Research on GPU under pressure shows that high-density scaling leads to these failures when internal heating reaches certain thresholds. This forces architects away from designs that simply pile more transistors together and towards systems prioritizing reliability over pure clock speed. The consequence of this shift is profound for how we build AI accelerators. You cannot just make the processor faster because memory access speeds have not kept pace with logic speeds. We are now facing what engineers call the memory wall, where the compute units sit idle, waiting for data to arrive from DRAM. Because raw transistor density yields diminishing returns in clock speed due to power constraints, we see a move towards specialized tensor cores rather than general-purpose arithmetic logic units. These dedicated blocks handle matrix multiplication far more efficiently because they are physically optimized for that specific workload without wasting energy on unrelated operations. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider the interconnect topology now becoming the defining factor in modern GPU design. Latency in data movement between cores dictates actual throughput, often more so than the number of transistors available. If you have a super-fast core but slow connections to its neighbors or memory, that speed is useless. This reality makes optimized placement of data over raw compute power the critical metric for success. We are seeing chiplets and on-package high-bandwidth memory replace simple die size increases because moving data vertically within the package is faster than dragging it across a large silicon surface. This brings us to a crucial insight that often gets overlooked in technical discussions. While physics dictates the ceiling of performance, real-world adoption requires balancing these hard limits with practical reliability metrics and system-wide data flow efficiency rather than focusing solely on individual component speed. Research into VR avatar fitting studies highlights that even with improved hardware, software-level optimizations remain crucial for user experience. Without efficient algorithmic placement to reduce compute load, raw transistor density yields diminishing returns in actual application performance. The gap in current evidence is telling us something important about the industry direction. We are moving from an era where bigger was better to one where smarter placement matters most. The specific architectural trade-offs between scaling limits and interconnect topologies like NVLink or HBM3 define whether a chip succeeds or fails in production environments. Engineers must now design with the understanding that every nanometer of shrinkage brings higher power density risks, forcing them to prioritize data movement efficiency over raw calculation speed. Think about how this changes your approach as an engineer learning production-grade development. You might assume that buying the latest GPU with the highest transistor count will automatically give you better performance for training models. But if the architecture does not optimize memory bandwidth or interconnect latency, that hardware is just a very fast engine in a car with flat tires. The physical degradation mechanisms mean that running those chips at maximum capacity continuously can lead to silent data corruption over time, ruining your entire training run without any obvious error logs until it is too late. This shift also explains why some AI accelerators perform better on specific workloads despite having lower theoretical peak performance numbers. They achieve this through intelligent placement of memory and computation units that minimize the distance data must travel. The system becomes a coordinated dance where every component knows exactly when to move, rather than a chaotic scramble for resources. This is why specialized tensor cores exist alongside general-purpose logic. They allow different parts of the workload to run in parallel without fighting over shared pathways. The lesson here is that physical constraints are only one part of the equation. Without efficient algorithmic placement to reduce compute load, raw transistor density yields diminishing returns. You cannot simply outsource your performance problems to hardware manufacturers anymore. The software layer must be aware of these architectural realities and structure data flows accordingly to avoid bottlenecks before they happen. This requires a mental model that integrates physics limits with system design rather than treating them as separate concerns. As you look at the future of AI chip architecture, expect continued innovation in how we manage heat and reliability alongside speed. The industry is moving toward designs where interconnect topology is more critical than transistor count because latency and data movement between cores dictates actual throughput. This means that the next generation of chips will likely focus heavily on reducing the distance data travels rather than just increasing the number of transistors available for calculation. Understanding these dynamics gives you a significant advantage when evaluating hardware or designing systems. You stop chasing raw specs and start looking at how data flows through the system, where memory bottlenecks occur, and whether the architecture prioritizes reliability under sustained load. This holistic view is what separates good engineers from great ones in an era where physics has become the ultimate constraint on performance. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.